Hi, today we are going to see about PID compensation, proportional plus integral plus derivative controller, PID controller. A PID controller is generally used in industrial control applications to regulate temperature, flow, pressure, speed, and other process variables. Closed loop control system with PID controller is shown in this figure. The transfer function of the PID controller can be found as T ds square plus Ks plus Ki by S. It can be observed that one pole at origin is fixed. Remaining parameters Td, K and Ki decide the position of two zeros. In this case, we can keep two complex zeros or two real zeros as per the requirement. Hence, PID controller can provide better tuning. In the, in the olden days, the PI controller was one of the best choice of control engineers because designing of the PID controller was a little difficult. But nowadays, due to the development of software designing of PID controllers have become a easy task. Example, against step input for the values of K equal to 5.8, Ki equal to 0.2 and Td equal to 0.5, its time response is shown in this graph. Compare figure with previous figures. We have taken values such that all the time response can be compared. General guidelines for designing a PID controller. To obtain the desired response are as follows. Obtain the transient response of closed loop control function and determine what needs to be improved. Insert the proportional controller. Design the values of K through Ruth Hurwitz or suitable software. Adding an integral part to reduce steady state error. Add the derivative part to increase damping. The derivative part will reduce overshoots and transient time. Scissor tool available in MATLAB can also be used for proper tuning and to obtain a desired overall response. Note that the above steps of tuning of parameters are general guidelines. There are no fixed steps for designing controllers. Activity. A problem with example. Increase the quantity until you get to the set point. Increase the quantity means increasing temperature, angle, speed, etc. If too much, reduce the quantity until the step point. Closed loop controller is shown in this figure. The input is set point, which gives error signal. The output is fed back to the input side. The input set point and the output gives an error signal. The error signal is given as input to the controller and it is given to the system and we get the output. Closed loop system is set here. It is a closed loop because it has feedback. The output is measured at a certain frequency. The signal generated at a signal frequency. PID controller is shown in this figure. In this figure where R is the reference point or set point, B is the feedback value, E is the error signal, M is the manipulated variable, C is the controlled variable or process variable, and FCE is the final control element. Analysis. The additive combination of proportional, integral and derivative control actions is known as PID controller and is given by M minus M equal to KCE into T plus T square divided by 2Ti plus Td. The graph shows the difference between PD and PID controller. By using all three control algorithms together, process operators can achieve rapid response to major disturbance with derivative controller. Hold the process near set point without major fluctuations with proportional controller, and eliminates offset with integral controllers. The table shows the controlled variable and how the PI and PID controller works for the controlled variable. Summary of P controller, PI controller and PID controller. Thank you.